James Clerk Maxwell derivation of light equation. We know light can behave as a wave, which is what we call classical, or light can behave as particle, and we call that quantum. We know that light can be both particle and wave, and will behave either depending on the circumstance. Light is electromagnetic, radiation, or wave. It has a property which is known as transverse wave, where the electric field and the magnetic field oscillate perpendicular to each other and in the direction of the wave. And here's a function of transverse wave. The electromagnetic wave consists of radio wave, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. We have the wavelength in meters and the frequency of each electromagnetic wave. For visible, we have red, orange, yellow, green, blue, indigo, violet. The frequency increases as you go from the radio wave all the way to gamma. Energy increases from radio wave to gamma, and the wavelength decreases, as you can see, it's decreasing from radio wave to gamma. We're going to talk about two important quantities: scalar, which is magnitude, and that means size. Example, if a distance is 5 meters, that's scalar. Or you might say a vector quantity is the second one, which is magnitude plus direction. Example, 5 meters north, that's magnitude and direction. This is displacement, this is distance. Or minus 5 plus 5 because it's showing direction. Two ways of multiplying vectors. One is to use dot product, and dot means there's a dot in the middle of the two vectors. Multiplying vector in the same direction, we use dot product. A dot product will give you a scalar value. The second way is to use cross product, and a cross product means it's got times in between the two vectors. Multiplying vectors that are perpendicular to each other, we get another vectors. So when we use cross product, we get a vector. When we use dot product, we get a scalar value. Dot product. A dot product is also called scalar product because you get scalar value. In the case of energy, energy is work done, and work done is force times distance. Because they're in the same direction, we use a dot product. If I have a force pushing this object from a distance to that distance, then the work done on the object will be the force dot the distance, and that can be written as force in the x direction times the distance x plus force in the y direction times the distance y plus force in the z direction times distance z. This is for a 3D calculation. 1D, that's one dimension. This is for 2D, 2 dimension, and that's for 3D, 3 dimension. To apply the dot product to a force at an angle, we need to resolve this force here to be in the direction of the distance, because that force is pushing that object along, so they will be in the same direction. And to resolve that, we need to apply trigonometry, and that will be f cos theta. If it's for the vertical, it will be f sine theta, but we're looking for the horizontal. And to calculate work done will be equal to f cos theta, that's the force pushing that object, dot d vector, and therefore d can be brought to the front, the energy equal to f dot d cos theta. For cross product, which is also called vector product, if we have two vectors at right angle to each other, we can cross them, and that is basically, example is taking moment. So if you take moment from f to d, so that's turning effect, or you might call it torque. The work done will be equal to the force times the perpendicular distance, sine of an angle between them. Theta is 90 degrees because they're perpendicular to each other. Sine 90 equals 1. That will become f cross d. We need to talk about gradient. This is gradient with respect to x. Gradient is an operator. This operator is going to operate on a function. Let's give an example. If you have a function y equals function to the power of n, where f is a function of x. So this is one variable. That's why we said d over dx, because the function is just one variable. We can calculate the gradient by saying dy over dx, that's the y, which is equal to calculate gradient of a single variable. Let's give an example. Y equals x squared. So f is x, n is 2. So we're going to plug this into here. So we can say dy dx, we're applying the operator on y. And that will be equal to the operator on y. That's y. And that will be equal to, we bring the 2 down, that's a 2. And then x, which is f, then 2 minus 1 in the exponent, times the x dx, because x is f. The x dx is 1, so we're going to get 2x to the power 1. 2 minus 1 is 1 times 1, which is 2x. So that's what we call gradient. So gradient is to find the slope of a function. Now we're going to talk about a function with more than one variable. If we have a function u with more than one variable, x, y, and z, to the power of n, we can't find the gradient by doing something called partial derivative with respect to x by keeping the other two variable constant. That's why we use this symbol, do by, or partial derivative with respect to x, because we're keeping y and z constant. Partial derivative of u with respect to z in the direction of z. And we give it a symbol, that symbol indicating that gradient for the partial derivatives. This is in 3 dimensions. This is in 1 dimension, this is 2 dimensions, and that's 3 dimensions. And that equals to the partial derivative with respect to x while keeping y and z constant in the x direction, plus the partial derivative with respect to y in the y direction while keeping x and z constant, plus partial derivative with respect to z in the z direction while keeping x and y constant. And we call that symbol altered, or you might call it del, or you might call it Nabla. You square that, and that squared is called Laplacian operator, because these are operators. That's an operator. So this squared, if you square that, we call it Laplacian operator, which is going to be second order partial derivative with respect to x, plus second order partial derivative with respect to y, plus second order partial derivative with respect to z. And we also use another word which we call div, which stands for divergence. So I'll show that in a minute. But first, I'm using S for scalar, V for vector, and F for field. So if I do a partial derivative with respect to x, this will be the formula that I'll be using. Same thing with partial derivative with respect to y. That will be the formula I'll be using. You can guess the partial derivative with respect of a function u will be, again, you do the, because the function is f, and then you want to differentiate what's inside the function. If we have a del or Nabla next to u without any dot, we call that grad, which stands for gradient of u. So we're finding the gradient of u. That's what that meant. We have scalar field and we get vector field. So that will be a scalar field. Then we get vector back. We apply that onto a scalar. That's what this is saying. And then we get vector back. If you have a del dot u, that's a dot product, we call that div. And div stands for divergence. Again, we only apply div to a vector and we get scalar field back, which is get a number. Finally, if you have a del and you cross it with u, that's vector product. We call that curl u. We only apply it to vector and we get vector back. If you have a function, which is that function, I'm going to find partial derivative with respect to x. So we bring the 4 down, that's what this is. So you got a function there, you're doing this. So you bring the 4 down, and that's a 4, that's what that is. N is 4. And then you decrease that by 1. So you get a function there, you decrease it by 1. 4 minus 1 times the differential of that, derivative of that with respect to x. So this will be constant. So that the 3, so you bring the 3 down, still using the same thing, bring the 3 down, and then 3 minus 1, so 3x squared. And then you leave these there because they're constant. Okay, let's do the same for, and then we simplify it. 3 times 4, 12, and 3 times 3, 9, plus 2. Same base, you add the power. 3 times 3, 9, plus 2, 11. And this one will be 3 times 2, 6, plus 2, 8. And that will be 3 times 1, 3, plus 1, 4. So that's correct. Or you could just multiply this out. 4 times 3, 12. 4 times 2, 8. 4 times 1, 4. and then you differentiate. You get the same thing, differentiating that, so it'll be 12, and then you decrease it by 1, and this will still be the same. 4 times 2, 8, 4 times 1, 4. Let's try this. Differentiate u with respect to y, keeping x and z constant. 4 times, you bring the 4 down, and then 4 minus 1, and then you get 3. 4 down, 4 minus 1, 3. And then you want to differentiate what's inside with respect to y, keeping that and that constant. So 2 down, then 2 minus 1, so you're going to get 2y minus 1. 2 minus 1 is 1, and then you got the x cubed z. Okay, and then you can multiply them out. 3 times 3, 9. 9 plus 3, 12. That'll be 4, so that'll be 2 times 4, 8, x to the power 12. The y is 3 times 2, 6, plus 1, 7. Z is 3 times 1, 3, plus 1, 4. Or you could, again, multiply them out and differentiate with respect to y. So now it'll be 4 times 3, 12, x to the power 12. 4 times 2, 8. But you're differentiating y to the power 8. So you bring the 8 down, and then that'll be 7 left. 8, 7. 4 times 1, 4. So you could do it that way as well. Finally, the u with the z equals to, again, 4 down, and then 3 left, 4 down, and 3 left. Then you want to differentiate that. If you differentiate z to the power 1, 1 down, 1 minus 1, 0. Z to the power 0 is 1, so you just get 1. So that you just get your x cubed, y squared, and 1. So you don't need to write that. And then you can multiply them out. 3 times 3, 9. 9 plus 3, 12. That's 4 times 1. That's 4. X to the power 12. 3 times 2, 6. Plus 2, 8. Y to the power 8. 3 times 1, 3. And there's no other z. So z cubed. You could have differentiated straight away from here. 4 times 3, 12. X to the power 12. You're not differentiating that. 4 times 2, 8. 8 to the power 12. You're not differentiating that. 4 times 1. Z to the power 4. Bring the 4 down. And then 4 minus 1, 3. So that's the 4. 4 minus 1, 3. That's the 3. So either way, this is the partial derivative, because we got more than one variable. We're going to look at 4 Maxwell's equation. Maxwell combined some of the electric field and magnetic field laws into laws to create 4 classical electromagnetic theory equations. These equations tells us what light is. The first equation is called the Gauss Law of Electrostatics, and we have the divergence of electric field is equal to the density over Epsilon-nought. First of all, we're going to use charge equals to IT, and the unit for current is I is current, T is time. Unit is ampere seconds. Also, we know F equals to MA, and the unit for that is kilogram meters per second squared. The Epsilon-nought is the electric field permittivity of free space of the material between the two charges, and the Epsilon-nought in vacuum, and that has a value of 8.854 times 10 to the power minus 12 farad per meter. F stands for farad, which comes from Faraday's or microfaraday's name, and M for meter. Unit in base SI unit. Epsilon-nought formula is Q1 Q2 over 4 F pi r squared. Therefore the unit will be Coulomb squared, because unit for charge is Coulomb squared, over F is Newton, and R squared is meter squared. And that can be written as C squared n to the power minus 1 m to the power minus 2. And Coulomb is charge, which can be written as AS, so that's AS squared, because that's what Coulomb is. That's Coulomb. Unit for that is Coulomb, and AS squared. The Newton is kilogram meters per second squared to the power minus 1, and meter to the power minus 2. And that can be written as kilogram to the power minus 1, minus 2 times minus 1 times that. This is 1 times minus 1 is minus 1. That's minus 3. Minus 1 times minus 2 is plus 2. Times another 2, that's 4. A squared, that's A squared. So that's the SI unit for epsilon. 1 Faraday or 1 farad is equal to per kilogram per meter squared S to the power 4 A squared. F per meter We know what that is. This is F per meter. So take 1 M out, then you're going to get the unit of 1 Faraday because it's F per meter, which can also be written as I squared T to the power 4 over M R squared, because that's time to the power 4, current squared, 2, that's 1 over R squared, 1 over mass, M is mass. That's the distance here. And that can also be written as coulombs per unit volt. From the Maxwell first equation, we know what del is, altered or del or Nabla, and that's the value for that. Rho is the density, is the charge in a closed volume, because density is mass over volume, and the mass in this case we're looking at is a charge in a volume. E is the electric field, therefore the divergence of electric field, E, is describing a positive charge. Let's look at a positive charge. These are the lines of electric field coming out from the source. We call that a source. It's a bit like a water leaking from the ground, and the water coming out will be coming out in all directions. That will be the source. Same thing with a positive charge. Electric field always come out from the positive charge, and so that has a positive divergence, and that's what this is describing. And that's what divergent is. A source where something is coming out of it with a vector field. We also have a negative divergence where the fields are going into a point which we call a sink. It's a bit like water running down to a point in a sink into a plug hole. So that would be a negative divergence. That's what this is describing. So we have a point charge with a divergence, and that's a source. And if it's a sink, it will be negative divergence. From the first equation, we saw that the divergence of electric field is the rho over epsilon-nought. This gives an idea about the relationship between static electric field and electric charge. This is talking about the total charge coming from a point charge is equal to the divergence of that electric field. Here is a point charge again, the source, and this source has a charge which we call monopole. It's only got one pole, positive pole. Mono means one pole. The pole is positive here, and there's only one pole. So charge, monopole. So divergence has a monopole. For the sink, it also has a monopole. It's a negative charge where the fields are coming in to the charge. Here the fields are coming out of the charge. So this is divergence. This is convergence. If you're using divergence, that's positive and that's negative divergence. And note that this monopole only exists in electric field. And so this is calculating the total charge of that field, the net charge. The second equation is the Gauss Law of Magnetostatics, and the scientist behind it, the German mathematician and physicist Carl Friedrich Gauss, that the divergence of magnetic field is zero. The magnetic field, it's a dipole, magnetic dipole, which means that the field is coming from the north and going into the south. These are magnetic fields. So B stands for magnetic field, no magnetic monopole. Unlike the electric field where you have an electric monopoles, we don't have a magnetic monopole here. We have a magnetic dipole, no magnetic source or sink separately. So the total net of magnetic field coming out is equal to the total net of magnetic field going in. Therefore, the divergence of magnetic field will be equal to zero. And that's what this is saying. Because we don't have a magnetic monopole, nor do we have a magnetic source or sink separately. We have them together. The net outflow of magnetic field from a closed source, zero. The third equation is the Faraday's law of electromagnetic induction. And this is Michael Faraday, English scientist. And it says that the coil of electric field is equal to the change in magnetic field over time. It means that electric field can be created from changing of magnetic field. Coil of an electric field, that's what that is. Creating the electric field by changing the magnetic field. A magnet in relative motion with respect to a coil which will create a changing magnetic field which then create flow of current in that coil. And here is the coil and the voltmeter to detect the voltage created, or you can use the ammeter to measure the current. By moving the magnet bar in and out, we create a change in magnetic field. And that's what this is saying. But don't forget, the change in magnetic field is being created to oppose that, what is causing it to change. That's why it's negative. The fourth law, or the fourth equation, is the Ampere and Maxwell law. It is the Ampere and Maxwell had to tweak the equation, and it became Ampere-Maxwell law. And this is where the coil of magnetic field equal to the ampere current and the change in electric field. This is looking at a current through a wire with a magnetic field being created, and as B stands for magnetic field, and this is the wire, conducting wire. Using right hand rule, the Mu-nought is called the permeability of free space of the material. Nought is referring to vacuum. Mu-nought has a value which is 4 pi times 10 to the power minus 7, and the unit is Henry's per meter. I is the current, which is measured in amperes or amps. Unit of mu, which is Henry's per meter, which means Henry's over meter, and that's equal to Henry's per meter. Henry is an inventor of precursor of the electric doorbell and electric relay. H is equal to kilograms meter squared over second squared amp squared, which is Newton's meter over amps squared. That can be written as Tesla meter squared over amps, which is Weber over amps, or second squared over Faraday, or it could be written as Ohm over Hertz, which is Ohm second. The SI unit of mu is kilogram meter seconds to power minus 2 amps to power minus 2. That's T for Tesla, WB for Weber, H for Henry, F for Faraday, A for Ampere or amps, N for Newton, omega for Ohm, HZ for Hertz. The fourth equation is saying that we can create magnetic field from the current and changing electric field. We can create magnetic field from the rate of change of electric field. That's electric field over time. Summarizing all the four equations, for the electric field, we have the divergence of electric field is equal to the density of charge over Epsilon-nought. And we have the coil of electric field equal to change in magnetic field. For magnetic field, the divergence of magnetic field is 0 because there's no magnetic field monopole. And for the coil of magnetic field, will be equal to the current plus the change in electric field. So the laws are Gauss for the first one, and Gauss again for the divergence, and for the Faraday electromagnetic induction, and Ampere and Faraday's law. The electric field can be generated not only by the presence of charges, but also by changing the magnetic field. The magnetic fields can be generated not only by the presence of electric currents, as the magnetic field can be generated by not only the presence of electric current, but by changing of electric field. Maxwell shows that light is electromagnetic oscillation. Electro meaning electric field and magnetic field oscillating perpendicular to each other. We need to find the coil of electric field. So we're using the equation number 3, finding a coil of electric field. To do that, we need to apply a vector field identity. And the vector field identity is a coil of vector A can be written as the grad, so that's the grad, that means the gradient of divergence of A vector minus the Laplacian of A. So Laplacian is the square of this del, and we need to apply that to this one. So we got a coil of electric field. We got coil of electric field here, and that will be equal to the grad of divergence of electric field minus Laplacian of electric field. And that should be with a vector on top, direction. So that's the identity we need to apply. Now we need to find out what this is. Okay, so we are finding the coil of electric field. We're applying the coil to equation 3, and this is what we got. We got that. We're applying that, and we got the grad of divergence of electric field. We're applying the identity minus the Laplacian of electric field. So we need to work this out and work that out. In order to do this, we need to do it in vacuum, which means we're doing this in vacuum, which means the density of charge will be 0, so there'll be no charge and no current. We would have the coil of electric field. We know what electric field is, that one. So we're going to replace that with this. Okay, so we replace that with this, which is there, equal to, now we got the divergence of electric field. The divergence of electric field, because we know density is 0, so that will be 0. So we're going to get that the grad of 0 is that 0 minus the Laplacian on electric field. This is what we got so far. Bring coil in. So we got the minus out. So that minus comes out. Now I want to take the coil inside here and bring the partial derivative with respect to time out. So that's the partial derivative with respect to time. What's left is the coil of magnetic field. We don't know what the coil of magnetic field is, that one. That equals to the minus the Laplacian of electric field. At the same time, we got the minus partial derivative with respect to time, and we're going to write this here. So that's that one here, into replace that with that, and that equals to minus Laplacian on electric field. Okay, so this is where we got to. I is 0, so that's 0 here. We've only got that left, so that goes in there. And now we need to bring this out and take that back in. So we're taking these two out and took that in. That times that will be partial derivative times partial derivative will be partial derivative squared. Partial derivative with time times partial derivative with time will be partial derivative with time squared. And then we've got the E, electric field. So that is an operator on electric field, and that equals to minus Laplacian on electric field. The minus cancels the minus, so that is equal to that. So that's our first equation. Finding the coil of B using equation 4. We've done it for equation 3, so we're now going to use it for equation 4. This is the coil of B. But first, we need to apply the vector identity again. When we have a coil of vector A, we get the grad of divergence of A minus the Laplacian on A. So we need to do the same thing here. So that will be equal to the grad of divergence of B minus the Laplacian on B. And that, we need to write this out. It's this one here. But I is 0. So that will be 0. So that goes in here. So that will be equal to the coil, which is that one. And we need this, which will be the I-naught plus the change of electric field. But we know that's going to be 0, equal to the grad, which is 0 here for the divergence of B minus the Laplacian on B. This is where we got to. And now we're going to make that 0 because there's no current. Mu-nought in vacuum, charge will be 0 and current will be 0. And then we get, don't forget that 2 will be 0 because this is 0. So we get that and this, and that equal to minus Laplacian on B. And that comes out and that goes in, so we get the coil of electric field, and that's that. And that equals to the negative Laplacian on B. This is where we got to, and now we need to write this out. So we got that, we're going to write that out, which is this one here, which is that. So we write this and put that in. We replace that with this, and that equals to minus Laplacian on B. and that equals to, we go minus, take that minus out, then you multiply that with that, multiply that with that. Mu-nought epsilon-nought times partial derivative second order with respect to time on B field, and that equal to minus Laplacian on B. The minus cancel minus, and then we get the Laplacian on B equal to mu-nought epsilon-nought second order partial derivative on B with respect to t. So that's our second equation. But remember the first equation, this is the first equation, and that's the second equation. We're going to compare that. The equation A and B are equations of wave motion. Wave equation in one dimension, we have a function f, and the wave equation in x direction, where the particle is being displaced from rest position to a maximum. We can write the wave equation for that of the function. Partial derivative of the second order with respect to x will be equal to 1 over c squared partial derivative of f with respect to t. F is the disturbance, that is the displacement from rest position. X is direction of motion. C or V is the speed of wave. Wave equation in 3D, we write the Laplacian f will be equal to 1 over c squared second order partial derivative f with respect to t. And we know that's the Laplacian operator, so we can change it to the Laplacian f equal to 1 over c squared second order partial derivative f with respect to t. Del squared equals Laplacian operator. Right. From the wave equation in 3 dimension and Maxwell A and B, if we compare this equation to the wave equation, we can see that the Laplacian and Laplacian apply to electric field and magnetic field, and the second order partial derivative with respect to time in both right hand side. The common ratio here will be the epsilon-nought and mu-nought here, both will be equal to 1 over c squared. So that and that correspond to 1 over c squared. We know the value for mu-nought, 4 pi times 10 to the power minus 7 henries per meter, and for the epsilon-nought, 8.854 times 10 to the power minus 12 farad per meter. 1 over c squared correspond to mu-nought epsilon-nought. C squared equal to 1 over mu-nought epsilon-nought. If we square root both sides, we get c equals root 1 over mu-nought epsilon-nought. We can rewrite that as c equals 1 over root mu-nought epsilon-nought. And if we plug in the values here and there into there, we will get c equals to 299792458 meters per second, which is approximately equal to 3 times 10 to the power 8 meters per second, which is the speed of light. Electromagnetic disturbance propagating through vacuum with the speed of light, because light itself is an electromagnetic disturbance. E here is the electric field moving up and down. We've got the B here, which is the magnetic field moving perpendicular to the electric field. In 1888, Heinrich Hertz was a brilliant German physicist and experimentalist who demonstrated that the electromagnetic waves predicted by James Clerk Maxwell actually exist. Hertz is also the man whose peers honored by attaching his name to the unit of frequency.